So we just got finished seeing a visual of a supposed link between the acceleration vector of a vector function and the unit tangent and the principal unit normal vector. So I was visually showing you about a concept. In this little segment, we're going to see a proof. It's going to fall short of all of the usable pieces we will need, but it's going to clearly show that when it's all said and done, acceleration can be found by a linear combination of tangent and the normal vector. So let me just show you some notation here. This is a scalar, a multiplier, as is this. This could be called the tangential scalar for acceleration, and this would be the normal scalar for acceleration. You can just think of it as the constant that goes with tangent and the constant that goes with the normal vector. We'll see supposed formula for these two when we're finished here, but they will not be the most usable. They need a little bit modifying. So that will happen in another segment. This is going to be just a proof that the tangent and normal vector can make acceleration if added in a combination. So here we go. Math majors, this is the kind of stuff that excites us. Algebraic derivations, there won't be many more of these moving into our math future. The types of proofs grow more complex, but every now and then we derive algebra formulas for something. So here we go. When we take the velocity vector and divide it by its magnitude, we get the unit tangent vector. That was its definition. Now, that means that I could say that the velocity vector is equal to the magnitude of velocity times the tangent vector. Why would I do that? Well, the silly algebra teacher in me says because I don't like fractions that much. But what we're going to do is we're trying to find acceleration. And I know where acceleration comes from. Acceleration is the derivative of velocity. So if that's the case, then acceleration is the derivative of the velocity vector. And if I take the derivative of velocity to get acceleration, let's take the derivative of this expression. And to do that, I'm going to first write a notation that might not be a common derivative notation, but it's one that many textbooks use. We're just going to use a capital D for derivative with respect to t as our variable. We're going to take the derivative of that expression. So this just means I'm going to take the derivative of this. That's all that says. Now this is a type of product, but it's a scalar multiplied by a vector. It's not in this set of videos at the moment, but it may be sometime later. So if you're watching this video 3 years from now, maybe there will be a video for it by then. But the proof of this little product rule won't be covered right now, but it looks a lot like the product rule as we know it. It's going to be the derivative of the magnitude of velocity times the tangent vector plus the magnitude of velocity times the derivative of the tangent vector. It's a product rule. But with a scalar and a vector, you can't just assume those products work like they did at the beginning of calculus. But it does happen to be true, just won't be proved right now. Now, I'm going to just point out to you that when you take the magnitude, you have a scalar, and this is going to be a scalar. And part of my objective was to have some scalar multiplied by the tangent vector, and there it is. Some scalar multiplied by the tangent vector. But this is not a scalar times the normal vector yet. It's close, but it's not quite there. So I'm just going to call this a sub t. That part of the mission has been accomplished. And I'm going to do a little magic trick here. Magnitude of velocity. Some math magic. I'm going to multiply the numerator and denominator by the magnitude of t prime. Magnitude of t prime. So when you multiply the numerator denominator by a non-zero value, you're multiplying by 1, because that's equal to 1. It's just an ugly 1. And please note that this is the principal unit normal vector. That's the definition. So once again, I have a scalar multiplied by, in this case, the normal vector. So I truly end up with acceleration is some scalar times the tangent unit vector plus some other scalar times the principal unit normal vector. The visual for this is more significant because it shows that they're all in the same plane. But you need to know how to do it algebraically for what we're going to do next. Now, I will define these, provide some formula, but there's more than one formula for each of these, but I'll show you what I would consider the least painful versions of these. And ultimately what we're going to do is we're going to use this equation not to find acceleration, but we're going to use it to find the very messy principal unit normal vector. We're going to sneak in around the back and solve for n this way, but not in this segment. Until next time.